Alice and Bob arranged to meet for lunch on a certain date. We're giving this information. However, neither are known for their punctuality, so we have that they both arrive independently and uniformly at a certain time between noon and 1 p.m. on that day, and each of them are willing to wait 15 minutes for the others to show up. And the question is, what is the probability that they will meet for lunch that day? Okay, so let's write out the information that we are given. So let Alice be the random variable, arrival time be random variable A, B be Bob's arrival time. We're given that they are uniformly arriving between noon, which is 0 here, and 1 p.m. which we set to 1. So essentially we have a uniform distribution with the x-axis being 0, 1 here being just 1 from the support of the uniform, which represents 1 p.m. And here we have 12 by noon. All right. And now we were asked, what is the probability that they will meet? And this can be seen that if Alice arrives at, say, 12:15, then she is willing to wait 15 minutes, which is that Bob has to arrive somewhere here. So this is Alice, this is Bob. So their difference in absolute terms have to be within, it's a distance of 15 minutes. So this can then be expressed as the absolute value between A minus B, because we're looking for a distance, and this is 15 minutes. What is 15 minutes? Well, let's write this as 15 minutes. Let's now just translate this to the uniform distribution. This means A minus B half. Well, that means 1/4, right? Because 15 is a fourth of the uniform distribution. All right, so now what we want is the probability of this event happening. Less than 1/4. All right, and this is the answer that, well, this is the problem that we are aiming for. So let's. There are different ways of solving this problem, and the way I'm going to tackle this is starting with a visual, and then we're going to try an analytical version. I'm going to show you an analytical version of this issue here. All right, so let's draw it out. So let's look at the three-dimensional version of this problem. So we have then, let's put the a variable. Let's put this little a, and then we have A, we have B, and then we have the probability, which is actually the CDF. This probability here is the CDF. So this is of this event occurring. So let me write this as the event of A, B, like so. And this is actually what the third axis is representing. And we have the origin, which is 0. To write the 0, and this is 1 here. This is 1 there. And now we have a domain that looks something like, oh, a little short. Let me put it out like so, like that. And what we're then looking for is, and actually, you know what? Let's draw out the domain only to be a little bit more precise, and then we're going to map this back here. So the domain, I'm going to put the B. So we're going to have A and B. So basically, this just flipped this one into this two-dimensional sheet, and then we have one here, we have one here, this is 0, like so, and this is the green area that I just drew. This is the domain. Okay, now let's figure out what part of this domain represents the event of interest, which is this event here. Okay, so let's continue ahead here. So what does this probability, what does this absolute value mean? Well, let me just write this out, that this basically means that we have two events when we write out the absolute value. So we have the event, let me move this down a little bit like so, and this represents basically two things when this is positive. So positive A minus B less than 1/4, and then we have the other version, which is minus A minus B less than 1/4. And I'm going to write both of these. I'm going to plot them out here. Just after some simplification, I'm going to express these two in terms of B, just because it's easier than to draw the two lines of interest that will show the region where this event is true. Okay, so this means this is equivalent to then A minus 1/4 B, like so. And then we have the other region, which is basically like, so we have minus A plus B less than 1/4, and this whole thing means B is less than equal to 1/4 plus B, like so. All right, so we have now expressed both of these in terms of two functions, which is that we have an event where B, which is Bob in this case, has to arrive when this is true. So whatever value A takes minus 1/4, and then B plus 1/4, and this should not be a 5. I'm not sure where it got the 5 from. Sorry about that. It should be an A. Okay, let's draw now out these two lines and see what we get. Let me start with the first one. Call this just the first, and this is the second. And here we see that now we can draw this as, so when does if I have A equal to, if A is equal to 0, what is B then? Well, it would be minus 1/4, which is obviously outside of the probability domain. But this will help us figure out when it crosses. So this is 1/4 here, 1/4, and then whenever B is 0, well, obviously then A is 1/4. So there's a 1/4 here. So let's see, whenever A is 1, when does it cross this line here? So when A is 1, then b is 3/4, like so. So it means that this line is going something like that. Give it a little messy. Let me see if I can just draw a straight line like so. Okay, this looks good. And this is the function little b equal to a minus 1/4. And then we have another one, which is the second equation. And it's purely symmetrical. So when b is equal to 0, then when a is 0, b is 1/4. So when a is 0, so it will be crossing here, like so. And when a is 1, it will be heading up to 1 plus 1/4. So it's up here somewhere. Let's do that in blue too. Okay, and when I can draw it like let's see, just b is 1, right, with like up here, and when a is 0, it's up there, it's 1/4. Yeah, so let's do that like so. Okay, so now we have and this is b equal to 1/4 plus a, like so. Okay, so what does this region mean? Well, this region now here is the event of interest. Everything within that, and this could be seen if we write out this probability, now combining all this information, we have that b must be, so Bob, we're expressing this whole thing in terms of Bob, but it's, again, purely symmetrical. We can have add a there. So b has to be larger than this, and less than this, a minus 1/4, like so. Okay, and so it means that Bob, holding Alice's arrival constant, has to arrive in this region. This is the valid region. This is the probability we're looking for. Okay, and so how do we calculate this whole thing? This looks slightly a little convoluted, but we are now in the exercises related to joint marginal and conditional distribution. So we are asked here to think in terms of those things. One of I will solve this analytically. One of the easiest ones to think about is just to look at this visually and see what is it actually that we are trying to derive. Now this quadrant here is again, it's purely symmetrical. It goes from 0 to 1, 0 to 1. So we have 3 triangles, and then we have this area that looks, if we look at it, it actually consists of, we can do this in different ways, right? So we can either calculate this a little bit more complex shape, which has a triangle or here, there, and then has this region there. Well, I drew this one is a little ugly. It should be, again, symmetrical, like so, like that. the easiest thing to calculate is to calculate this triangle here and that triangle here. And we could essentially just use the Pythagorean theorem and do that like so, but I'm not going to do that. I'm going to use integrals because you will be facing more complex we'll be facing more complex problems later on. So I just want to make sure that we are getting the full logic here. So the full probability space is 1. Okay, and let me copy whatever we want to calculate, which is this probability here. Duplicate this, we'll put it here. Okay, so now I'm reasoning just purely logically. This is visual or geometrical derivation. So we have the full probability space, which is 1. Now we're going to subtract the first triangle and then the second one. And because they are symmetrical, I'm just going to calculate this and multiply it by 2. And then we end up with the region of interest, which is this probability here. Okay, 1 minus, so let's think about what is the first probability. Let's start with the inner integral. I'm going to derivate with respect to b first. The density, because it's uniform, is 1. And this, I'm now taking the integral in this direction. So we want all those slivers going in this direction, and that the upper limit has to be 1, right? But the lower limit is this function here. So this goes from 1 down to b equals 1/4 plus a. And the outer limit, we want this to go now from in the other direction. So we have now taken all the b's and the b slivers, and now we're moving in now in the a direction, which goes from 0 up to 3/4. 0 to 3/4, like so. Okay, this is this 3/4 here is when, well, as you see, I haven't drawn this figure purely symmetrically because this 3/4 should be up here, but you get the point. Okay, now there's another, right, so sorry, it should be a parentheses like so, and then there's a dA. And now we are subtracting off the other triangle, and that one, let's reason about it in the same way just to see if we fully, just to really write out every in detail. The inner integral, I'm going to integrate with respect to b. The density is 1 because it's a uniform, and here we're moving now again because we're doing this with respect to b first. We're taking all those small slivers like so, and that means that we're going from 0, that's the lower limit, up to this equation up here. So it's a minus 1/4, 0. We have the outer limit, and the outer limit, it starts at 1/4. Sorry, let's see, it's at 1/4 here. Yes, it's 1/4. Again, sorry about the disproportionate figure like that. But it goes from 1/4 up to 1. Okay, so 1/4 up to 1. Now it's time to calculate this thing. So 1 minus, and then let's start with the inner, as I said. Here we have that is then b. 1/4 plus a up to 1. 0 3/4 dA. Just going to write out this negative like so. Dot dot dot. Minus in this inner thing is now 1 minus 1/4 plus, sorry, it should be negative. Negative a. Okay. And so now we take the integral of this expression here. And that end up being, so this one here is, now we are integrating with respect to a, so that's an a, minus 1/4 a, and then we have minus half a squared, like that. From 0 to 3/4. Okay, and that is 1 minus 3/4, 1 4 3/4 minus half. We have the square, so we're 3/4 is 9/16, like so. Okay. Yep, that looks correct. Just double checking it, and now we have the minus dot 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 minus dot dot dot. So that's the other integral here. That should have the exact same area because of the symmetrical properties of these triangles. 1 minus, and let's just add everything up here before we move on. And green, this whole thing is now, let's see, so we have, let's start from the right, so this is 9/32, that's 3/16, and 3/4, like so. All right, so now we have to make sure that they have the same denominator. Just checking so everything looks correct. Okay. So to make this 32, and then we have minus 9. Here we have to take times 2, so this becomes a 6. And here we have to take time 4 times 2, so that's times 8. 8 times 3, 24. 24 minus, and this whole thing becomes now minus 15, 9/32. 1, 9/30. Oops. 32. Okay. And so what do we have? We have 9/32. But we have this other triangle, which is also 9/32. This is what the dot, so this is what the dot 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 is, without having to do this again, will lead to the same area because of symmetry. And now what do we have? We have 32. So that this one is just 32 divided by 32 minus 18. Minus 18, 32 And that is 1432. And simplifying this further, we have 7th of a 16th. And that is the probability that we're looking for this region here. And right. And there is, I mean, so there's another way to tackle this problem, which is to actually write out this whole thing. I'm thinking about the limits again, as we did. So we will be calculating this area. So what I can do here to verify that is that we can. So let's see. This is like this is a visual explanation that we just did. Let me take this, copy it, and put it here. Paste that. I'm just going to write that out, that integral, and then leave it up to you guys to solve it. But it's a good exercise to think about the same problem in two different ways, and there are several different ways of calculating this area. I mean, basically, you can calculate this whole thing. Remove that one, and then subtract off that one. So there are many ways of doing this, and I like to play with the different ways of doing so. So let me just write out, and I'm going to copy this figure here just to make it easier to see what we are doing. And so we have now, by this new, this term that I'm going to write out, capture this extra region there. Okay. So just peeking at my notes, just to making sure that I'm starting in the right. So let's start with then. So this expression, as I said, just we did this using that, subtracting off this triangle and that triangle from 1. Now, let's ask ourselves, divide this expression up in 3 terms instead of this lower part, that one, and this one. And these are again symmetric. Starting with the lower triangle, we have the integral now going from 0 to b being equal to a plus 1/4. Right, so we have we taking the derivative, and we have density 1 always for the integral. Sorry, I'm keeping on saying derivative of a. So we're going from 0 in the y direction up to the line here, and then over the x dimension we're going from 0 to 1/4. 0 to 1/4. Okay, that was the first triangle. Now we're taking this part, which goes all the way. It starts with this equation and hitting that equation here. So its inner limits are b equal to a minus 1/4. The upper is x plus, a plus 1/4. Density 1 over integrating over b first, integrating over a then. And what's the integral over b? Well, it's going from 1/4 up to 3/4, right? So 1/4, 3/4. And the last triangle is starting with the inner over b. Now that one is b equal to a minus 1/4 because of the variation now over the this is the lower limit, and then it goes up to 1 because it's going all the way up here. This is over 1 over b, then over a, and the a part is that it goes from 3/4 to 3/4 from here up to 1. 3/4 to 1. This integral, and I'm not going to do this again, but it will end up being the same thing, and I urge you, I encourage you to check that.